Okay, welcome to the fourth lecture on hidden Markov model. Right. So this is also going to be the very last lecture on hidden Markov model. Right. So before we start, a very quick recap of where we are. Right? So we have been talking about unsupervised learning for hidden Markov model. Right? So what's the setup for unsupervised learning? It's unsupervised. So in the training set, we are only given the X sequences, right? We have a bunch of X sequences. So there's no Y sequence attached to the X sequence because it's unsupervised, right? So the data set is unlabeled, right? So that's the first thing that's given to you. Second, you're also given a set of possible states, right? So in this case, for example, we are given two possible states, A and B, right? And your job is to learn the model parameters, right? You want to figure out the model parameters in this unsupervised learning setup, right? And of course, once you know the model parameters, you should be able to assign to each X the most probable Y. Is that okay? Right? By calling the decoding procedure, right? In the decoding procedure, if you are given the X input sequence and model parameters, you can produce the Y, right? So that's what you can do in the decoding procedure, right? Right, so that's basically the setup for unsupervised learning. And we said we can actually use the EM procedure to help us for learning hidden Markov model in an unsupervised manner. Right? So the first version of the EM is a so-called hard EM. EM comes with the E step and the M step. Right? In the E step, you are essentially finding the so-called membership. And in the M step, you are updating your model parameters. Right? So basically, you repeat the E and M, right, for multiple iterations, right, until you are satisfied. So before the E, you can assume you have an initialization step, or alternatively, you can say, I can imagine, right, I have finished my previous iteration same step. In other words, you should assume the model parameters are already given to you, right? So that's why you can run the VTB. In the case of hard EM, you are going to find the hard membership. So you are going to assign to each X input sequence a Y sequence. So naturally, you can call the VTB procedure, right? And after you finish the E step, right, your data set becomes fully labeled. For each X, you have a single most probable Y assigned, right, which is a sequence. And then you can go ahead and you do some counting, right? You collect the counts, right? So these counts are typically, they are always integers, right? So you pass such count information to the M step, right? And then you can go through the supervised learning procedure to estimate the most probable values for A's and B's. Okay, once you have the A's and B's estimated, you can return to the E, right, to run the VTB, right? And you can collect the counts information and then pass such information to the M step. Okay, right, and just repeat. And there's also a different way of performing EM, right? It's called a soft EM. As we said, soft EM turns out to be harder, right? And here, one important distinction between the two is the M step, they are the same, right? But for the E step, now you need to collect the so-called fractional counts or expected counts, right, from each instance, and then you pass such information to the M step. So that's the difference, right? And in the last lecture, we said we can actually use, we can calculate the alpha and beta scores, so forward-backward scores, right, to help us to calculate the count information efficiently, right? But we still haven't discussed what's exactly the algorithm that we can use here, right, for us to calculate the alpha and beta scores, right? But we know the name is actually called forward-backward algorithm, right? So in today's class, we are going to develop this algorithm together. Right? So keep in mind, all we need to do is to find a way to calculate the alpha and beta scores efficiently, right? And so that we can actually calculate the expected counts efficiently. Once we can do that, we can perform the entire soft EM procedure efficiently. Okay, that's our objective. Right, so how do we find the fractional counts? right? This is what we discussed essentially, right, in the previous lecture, right? We said eventually, right, to calculate the counts, we need to solve the two inference problems, right? So this is a so-called inference problem because we are interested in finding the probability for certain variables to take certain values given some other evidence, right? So later when we talk about Bayesian networks, you will see a more general formulation for the inference problem. Right? This is exactly an inference problem for Hitler-Markov model. So please note that here I actually abuse the notation a little bit, right? So in fact, I should have a superscript here as well, right? Should have a n superscript I here to indicate the fact that this n, right, is really the length of the ith instance or the ith sentence, right? So I didn't do that because I don't want to make things too complicated, right? So otherwise it's going to be very confusing, right? But you should know what I'm talking about, right? I'm looking at a particular instance now, and this n is actually the length for this particular instance, okay? Right, so similarly, we have a different inference problem here as well. And we went through some derivation in the previous lecture, and eventually we realized that you know, we can rewrite these two guys, right, in terms of alpha and beta, right? Okay, right. So now let's focus on these two first, right? So how do we calculate, for example, this is actually a simpler problem, right? So how do we calculate this condition of probability? How do we perform the inference, right? In the last lecture, we said we can rewrite this guy in terms of this divided by this, right? So the nice thing about you know, rewriting, right? Rewriting this denominator as something like this is because we want to make the two probabilities to be similar to each other, right? And you know, by making them to be similar, we can just focus on something like this, right? First. All right, so now let's look at what's upstairs here, right? So joint probability basically says, you know, yj takes a value u, right? So this guy takes a value u. In the last lecture, we said that we can actually, you know, introduce the alpha term and beta term here, right? Alpha term basically is a joint probability of everything in red here, right? And beta is essentially the conditional probability of these guys, given the fact that yj takes a value u, right? Okay, with the definition of alpha and beta, we should be able to rewrite this guy in terms of something like this, right? It's a product between alpha and beta, right? So then, similarly, right, for the denominator, we can rewrite it as something like this. Okay, and remember I asked you a question, right? It seems that this k is is arbitrarily chosen, right? So in other words, I can set k to 1 to 12 or something, right? And it seems that the value does not change, right? No matter which k I pick, right? I randomly pick the k essentially, right? So, you know, why that's the case? In other words, why this value is going to be the same no matter which k I am going to choose, right? So, okay, so this is going to be a question that I ask you to think about. And in today's lecture, right, we'll be talking about this problem. Okay. All right, this is for the first condition of probability, right? So the second condition of probability is something like this. And we can similarly, right, rewrite this guy in terms of something like this, and we can find the relation between this term and the alpha and beta. Right? In other words, we can rewrite this guy in terms of alpha and beta. Okay, so that's what we did. We can split the network twice, right? Okay, and this is alpha, right? And this is beta. Okay, as for these two black nodes, right, we can use emission, right, and a transition, right? Emission and a transition to take care of these two. Okay, right? So that's what's happening here upstairs. As for the denominator, it's going to be the same. Right? So that means you can actually, coming back here, right? you can actually rewrite this in terms of alpha and beta, and similar for this. Okay, right? So this is what we arrive at. Right? So since you can, you can rewrite that in terms of alpha and beta. Once you figure out a way to calculate alpha and beta efficiently, right? You can calculate the expected counts efficiently. Right? So remember, this is what we need, right? In the M step, right? You need to get the count information. Okay, right? So you can calculate alpha and beta efficiently, right? You can calculate AUV, right? You can update the model parameters efficiently. So the M step can be done efficiently, and the entire soft EM procedure can be done efficiently. But there's one more thing, right? So we haven't talked about this, right? So what about this count? Okay, so we talk about this count, right? This is exactly this count, right? But what about this count? Okay, right? So this is something that I hope you can figure out, right? So instead of telling you how to calculate this, right? You need to think about this problem by yourself. Is that okay? Right? So the answer is you can also rewrite this, right, in terms of alpha and beta. But how exactly are you going to do it? It's going to be something that you need to think about. All right, now we are here, right? So our job is to figure out a way to calculate alpha and beta efficiently, right? And this is our initial goal, and this is our current problem. Okay. Right, so actually in the last lecture, we figured out something interesting, right? In terms of the semantics of the alpha and beta scores, right? And we said, eventually, right, if you're talking about the very last alpha, right, the score of that particular very last alpha, right, which should be the alpha stored inside this node, right, should actually be the sum of the scores of all the paths connecting start and stop, right? So there are exponentially many possible paths, right, connecting start and stop, right? So what's stored inside this guy should be the sum of the scores of all the paths, right? So previously in Viterbi, it's a score of a single most probable path. Now you are replacing the max with a summation. Okay, so you are considering the sum of all the paths, right? So that's a very nice interpretation of the score, right, for the alpha. So in general, right, what's the semantics of this alpha? Alpha uj. So where is alpha uj, right? So we are referring to the node with state u at position j, right? So what's the semantics of the score stored inside this node? So it should be the sum of the scores of all the paths, right, connecting start and this particular node, right? Okay, because you are replacing the max operation, right, with the summation operation. Okay, and now the question is, right, how do we modify the Viterbi algorithm to calculate the forward scores, right? So that's the first question we want to focus on. Okay, if you haven't thought about it, right, so I suggest that you pause the video here, right, spend some time to think about the problem before we continue. Okay. All right, so now let's start. So naturally, right, so we probably want to move from the left to the right, right? The reason is we're calculating the forward probability, right? So it should be very similar to what we did for the Viterbi, right? So the only thing that's different is that we are replacing the max operation with the sum. Okay. Now, the first question I want to ask you is, what should be alpha u1? Okay, I'm talking about position 1 and the state is u, right? In other words, what should be the score stored inside this node? So we know what's the semantics of the score, right? Should be the sum of all the the scores of all the paths, right? Connecting start and this node. How many paths do we have? Just one path. Okay. So what should be the score? Right? So naturally there should be a transition. So is there anything else? There should be a transition from start to U, right? Is there anything else? That's a question, right? Is there emission as well? Okay. So to answer this question, right? So probably let's look at the definition of alpha uj, right? So this is alpha u1. That means the j sets it takes the value 1, right? So it's 1. That means we don't have any x here, right? So it's only y j is u. Okay. So that means do we have any emission? Do we generate x1? The answer is no, right? So yeah. So this is actually the value, right? That's that should be stored inside this node. Right. So yeah, alpha u1 is a start u. Okay, right. So another way to understand why alpha u1, right, only involves a transition is we can look at this picture, right? So remember, we need to cut, right, the network into 2, right? And the left portion gives you the alpha, right? So in this case, alpha basically refers to this part of the network, right? So the only node involved here is actually this node. There's no x1, right? So that's why alpha u1, right, is essentially, it only involves the transition, right? Only involves the transition. All right. Okay, so we are done with the base case. What about the general case, right? So what's the general case? Right, so let's say I'm interested in calculating alpha uj plus 1. Okay, I'm now here, right? I'm moving from the left to the right, so I should assume everything, in the previous layer, they are already calculated. So I probably want to refer to these values to help me when I calculate this guy, right? So what should be the recurrence relation here? So that's the question. All right. Okay, so what should we do? All right, you can think about it, but I can give you the answer first. All right, so the answer is something like this. Okay, so it says what? It says I visit the previous layer, right? I visit each of the nodes, right? Okay, let's say that the node here is V, right? I'm going to take the score here. The score is what? The score says, the score of the it's a sum of the scores of all the paths, right? Connecting start and this node, right? I'm going to take that score and I multiply the score with the transition from V to U, right? Similar to what we did in SUTD, right? And also emission, right? So now the emission is from this V to XJ, right? All right. So this is slightly different from what we did in SUTD, right? So in SUTD, our emission is from here, right? But now it's from here, okay? And then I take the sum, right? I have to consider all the possible cases. Okay, previously we did a max, now we do a sum, all right? So that's the conclusion, right? So you may ask, okay, why this is correct, all right? First, we can actually do a small derivation, right? So let's look at the definition of alpha, right? Based on the definition of alpha, okay? We want to look at the original definition of alpha is here, right? But I'm talking about alpha uj plus 1, right? Okay, I need to set, I need to replace j with j plus 1, right? So here I have xj and here is yj plus 1 is here, right? So this is exactly what's happening here, right? And I'm going to do a small trick. Okay, it's actually a trick that we are familiar with, right? I insert a yj is u, okay, at this particular position, right? And then I take the summation over v in front. Okay, I'm going to argue that this guy is going to be the same as this guy. Is that okay? Okay, so we are familiar with this trick, right? Pxy, if I add a summation of y in front, it goes to px, right? It's the same as px. All right. The reason I do something like this is because I want to factorize this joint probability, right? And please note that I inserted yj is v at this particular position, right? For some reason, right? Because I want to factorize this joint probability in a certain way, right? And I'm going to say, you know, the first term says I'm going to generate x1 up to yj is v, right, up to this point. In other words, I'm going to split my network, right? So it's from here, right, x1 up to this, and this guy takes the value v, right? Okay. And I have two remaining guys to take care of, right? But if you look at xj, right, how is xj generated? It's from yj, right? So, and we know the value for yj, right? And what about this? Again, it's generated from yj. So in other words, what I can do is something like this, right? I can rewrite this as something like this. So the first term basically says, okay. So the first term basically says, I'm going to generate everything from here up to this point, all right? And next I need to generate this guy, right? And if you look at this picture, xj is generated from yj, right? So it's sufficient for me to condition on yj is b, right? So by right, you should condition on everything here, right? But it's sufficient for you to just condition on this, right? Because if you look at this picture, xj is generated from exactly yj, right? And similarly, yj plus 1 is generated from yj, right? So it's sufficient for you to just condition on this fact. So the nice thing here is, if you look at the definition of alpha, this is exactly another alpha, right? So this is alpha vj, right? So what about this? This is a emission. So it's a bv bracket xj, right? And this is a transition, right? So it's from v to u, right? So it's a avu, right? Okay, so in other words, we arrived at the recurrence relation, right, between different alpha terms, right? So this is actually an alpha in the previous layer, right? In a particular node from the previous layer, okay? So yeah, this is a first way to understand the recurrence relation. And I have a different way that helps you to understand why we can arrive at this kind of a recurrence relation, right? So the idea is we can look at this graph and we try to split the network, right? So based on what we discussed before, right? We can visualize alpha by, you know, shading some of the nodes here, right? So if I split my network like this, and I set this guy to u, right? And alpha uj plus 1 basically corresponds to, you know, a joint probability that involves all these red nodes. Right. Okay, I want to draw the recurrence relation between different alpha terms, right? So what I can do is I can cut my network again, right? I can cut my network at this position again. And I set this guy to V, okay? And then naturally, right? This part of the network, right, will give me alpha Vj, right? Based on what we discussed. Now the question is, what's the connection between the two different alpha, right? So previously we have alpha uj plus 1, now we have alpha vj, right? So if we assume this guy takes a value v, right? And to reconstruct the original network, right? To reconstruct the original alpha, all we need to do is, you know, if we assume this guy takes the value v, we have to consider the generation of this guy and the generation of this guy. Is that right? So that involves what? That involves a transition from V to U and emission from V to Xj, right? But unfortunately, I don't know what's the value for V, right? So I have to consider all the possible cases for V, right? So we need to add a summation in front, okay? So we need to add a summation in front, okay, right? So we need to add a summation in front, okay? So essentially, this part says, to construct the original alpha term, right? We can take the alpha Vj here, right? We multiply it with a transition, right, from V to U, right? As well as emission from V to Xj, right? Okay. But we have to consider all the possible cases for V, right? Because we don't know what's the value for the previous node, right? So we have to take the summation part. And that gives me the original alpha Uj plus 1. Okay, that gives me the original network, right? That involves everything from here up to here plus this node. Okay. So that's a different way to help you understand the recurrence relation. Okay. Now let's focus on beta, right? So beta is defined as we have a definition, right? So it's actually a condition of probability. But we said we also have a semantic interpretation of the beta terms, right? If you look at this picture, right? Alpha and beta, they are kind of symmetric, right? So if alpha is defined as the score, the sum of the scores of all the paths, right? Connecting start and this node, right? So we can have a guess what's the semantics of beta. It should be the sum of the scores of all the paths, right? Connecting this node and stop. Okay, so it's a very elegant, right? Very symmetric. Now the question is, how do we calculate beta? Right. So let's start with the basic case again, right? So we are going to calculate the beta from right to left, right? So it's symmetric, right? And naturally, the very first step we have to think about is what's the beta un, right? So we are looking at the position n and we are looking at the state u. So what's beta un? Okay. So if you look at the semantics of beta, right? So it should be the score of the single path, right? So there's only one path. It should be the sum of all the possible paths, but it turns out there's only just one path, right? So it should be the score of this particular path, right? So naturally, it should involve a transition from U to stop. The question is, what else do we have here, right? Okay, what we can do is we can look at the definition, right? So J takes a value n, all right? J takes a value n, right? So it seems the only term left here is xn, right? And here's yn is u, okay? Yn is u. All right, so it's a conditional probability of xn given yn is u, right? So do we have another term? Besides the transition, we should also need to consider the generation of xn, right? From yn. So there is also emission, which is a bu bracket xn, right? So there are two terms involved. Okay. Again, we can understand why we have this base case, right? By looking at this graph, right? So as we discussed before, right? So we cut the network, we set the value for this guy to u, right? And this portion of the network gives me the beta, right? So let's see, what are the terms involved? There's a transition here, there's also emission, right? So that's why we have two terms here. Okay, right? So the transition specifically is the transition from U to stop, right? Remember, this is always stop. And the emission is, BU bracket xn, right? Okay, so that's a different way to understand the base case scenario, right? Now let's move to the general case. So we are moving backwards, right? From the right to the left, all right? So we are now here, let's say, right? We are at position J. So we should assume everything, here, they are already done, right? So we know the value inside this guy, right? So the value inside this guy should be the sum of the scores of all the paths connecting this guy and stop, right? And our job now is to calculate the sum of the scores of all the paths connecting this guy and stop, right? And we have to rely on the scores stored inside the next layer, right? You may want to call next layer or previous layer. It's up to you, right? Based on, it depends on your perspective. Okay. All right, again, so how do we do that? Right. Okay, again, I'm going to give you the answer first, right? So basically, it says, right, I'm going to visit the node in the previous layer, right? Okay, this is now my previous layer, right? And I'm going to take the score and I multiply it with a transition, right? Naturally, there's a transition from U to V, right? That's a score that you should consider. And also a emission, right? So the emission is from U to XJ, all right? Okay, so this is the answer, right? I can provide to you, right? So now let's see why this is correct, right? Again, I can do a small derivation, right? Similar to what we did for alpha. So based on the definition of beta, right? I can write down beta uj as follows, right? So it's a conditional probability of xj up to xn given yj takes a value u. Again, I'm going to play a small trick here, right? So this time I'm going to introduce yj plus 1 is equal to v, right? And I'm going to insert this guy at this particular position, all right? And I can add a summation over v in front, right? So if I do that, it goes back to the original conditional probability, right? So this is a trick that we have been playing all the time, right? Now, let's see. So it seems that the first thing we have to consider is how do we generate xj, right? So if you look at the picture here, xj is generated from yj is u, all right, good. So we need just emission probability here, right, to take care of the generation of xj, right? So what about this? Yj plus 1 takes the value v. How is this generated? From yj, right? So it seems that we need a transition parameters here, right, to help us with the generation of this guy, right? And what about the rest? Right. So remember, at this point, we have already generated xj and yj plus 1, which takes the value v, right? So let's look at xj plus 1. How is this generated? From yj plus 1. Do we know the value for yj plus 1 at this point? We just generated yj plus 1, right? Which takes the value v, right? So similarly for the rest, right? It's sufficient for me to know what's the value for this guy to generate everything, right? From xj plus 1 till the end, right? So in other words, I can rewrite this conditional probability as follows, right? So first I can generate xj given the fact that yj takes the value e, right? And next I can generate the value. I can generate yj plus 1 is v, right? Based on the fact that yj takes the value u, right? So here I need a transition parameter, right? A u v, right? Here I need a b u bracket xj, right? Right, so when I generate xj plus 1 to xn, right? By right, I should condition on this guy plus this guy and this guy, right? The two newly generated variables, right? But as we discussed just now, right? It's sufficient for me to just condition on this fact, right? Okay. That's because if you look at the picture, right, this guy is generated from this, right? So it's sufficient for me to just condition on this, right? So similarly for the rest, right? So it's sufficient for me to know what's the value for this. Once I know the value for this, right, I don't really need to care what's the value for this guy and the rest, right? Because, you know, I have very strong independence assumption here. All right, so yeah, we have managed to rewrite this conditional probability as a product of this tree. And we know this is a B, this is a A. What about this? Right, if you go back to refer to the definition of beta, you will realize this is actually another beta. This is beta V bracket J plus 1, right? So through this small derivation, we arrive at the recurrence relation between different beta terms. Okay, right. So this is the first way to understand the recurrence relation between different beta terms. And similarly, we can understand the relation by looking at this picture, right? So we are going to cut the network twice again, right? So the first time we cut is at this position, right? Okay, right? And we set the value here to be U, right? And if you do that, and the green part, right, gives you the beta, right? So that's beta U. This is a way to visualize beta UJ, right? As we discussed before. And then I'm going to cut again, right? Cut my network again, right? I cut it here because, you know, I'm actually moving from the right to the left now, right? So I want to draw the recurrence relation between the current beta at position J and the previous beta, which is at position J plus 1. Okay. If I set the value here to be V, right? So I arrive at, right? So this part of the network gives me beta Vj plus 1, right? Okay, now we are ready to draw the relation between these two beta, right? So the question is, how do we reconstruct the original beta here, right, from this small beta? So the difference here is, you know, I have these two nodes, right, that are not included, right, in this small beta. So I have to take care of the generation of these two, right, in order to reconstruct this beta, right? Okay. Now, how do we do that? So I have the beta Vj plus 1 here, right? To take care of the generation of these two, right? I first need a transition, right, from U to V, right? AUV. Second, I need an emission, right, from U to Xj, right? BU Xj, right? Okay, right. Are we done? No. So this is based on the assumption that this guy takes a value V, right? But in general, we don't know what's the value for this guy, right? If you go back here, right, you really don't have any assumption about the value for this guy. So in other words, you need to consider all the possible values for this guy. Here you are assuming, right, this guy takes a value V, right? To reconstruct the original network, you should consider all the possible cases. So you need to add a summation in front. Okay, so yeah, by doing this, you reconstructed the original beta term, which is beta UG. Okay. Right, so from here we can draw the recurrence relation between different beta terms. Right, so this is an alternative way for you to understand such recurrence relations between different beta terms. All right, so with this we are essentially done, right, with the forward-backward algorithm. Right, you are going to, okay, I'm not going to write down the pseudocode here for you, right, unlike what we did for Viterbi. But you should be able to understand what should be the entire procedure for you to calculate alpha and beta. For the alpha, you move from the left to the right to calculate alpha, right? For beta, you move from the right to the left. Okay, and this is a general recurrence relation, right? And we also talked about the base cases. Okay, so you may want to ask, what's the final cases? I leave that for you to think about, right? So it shouldn't be very difficult for you to figure out, right? So it's an exercise for you. So the next question is, what's the time complexity of the forward-backward algorithm? Right? Okay, let's see. Yeah, maybe I should still go back and rely on this picture. Let's look at alpha first. Right. So we calculate this score, right? In general, this I'm talking about a general case, right? So when you calculate the score here, right, you need to visit all the nodes, right, in the previous layer, right? So that means similar to Viterbi, right? You have T operations involved, right, when you visit the nodes in the previous layer, okay, in order to calculate one single score, right, in the current position. Right? And on the other hand, you have how many such nodes at the current position? You have t, right? So in other words, for each position, there are t-square operations involved, right? So you have n positions, right? So in total, the overall time complexity is going to be O n t squared, right? It's the same as the beta b, right? Okay, right? So similarly for the backward score, right? So we calculate the backward score. This is this case and general case, right? So when you calculate the score here, right, you have to visit all these nodes, right, in the previous layer. Okay, and in total you have t such nodes to visit, and on the other hand you have t nodes, right, in the current position, right? So for one position you have t square operations involved, right? Okay, and you have n positions, so the time complexity is O n t squared, right? So it's a symmetric, right? So the time complexity for forward and backward are exactly the same. All right. Okay, now coming back to the question that we discussed before, right? So in fact, before that, I want to ask you this question first, right? So we know the semantics of alpha and beta now, right? So alpha uj, right? I'm looking at this node, right? Alpha uj is the score of the, the sum of the scores of all the paths, right? Connecting start and this node, right? As for beta uj, right? It's the sum of the scores connecting this guy and stop, right? So my question for you is, what's going to be this guy? How do I interpret the multiplication between the two here? Right. Okay, so if you think about it, it should be the sum of the scores of all the paths, right? Connecting start and stop going through this node, right? Make sense, right? So there are many possible paths connecting start and stop, right? And only those paths that actually go through this node, right, will be counted, right? If you multiply these two, right, this is what you get, right? So it's a sum of the scores of all the possible paths connecting start and stop going through this node, right? So that's the semantics of this guy. Is that okay? Right. Now, if I add, right, so that's an explanation, right? So if I add a summation in front, what do I get? Right. Now I'm actually taking the summation over u, right? That means, it's actually considering all the nodes here. What do you get? Right. If you add a summation here in front, if you think about it, the semantics of this guy is going to be the score of the sum of the scores of all the possible paths connecting start and stop, right? Okay, yeah, just let me repeat. So if you add a summation here in front, right, this term, right, can be interpreted as the sum of the scores of all the paths connecting start and stop, right? Okay, right, so we have a nice interpretation of this. And then you quickly realize there's something very interesting. That means no matter which J you choose, right, the score is going to be the same because it's a score, right, that involves all the paths connecting start and stop, right? So no matter which J you pick, right, the score is going to be the same, right? So that explains, right, so this is the semantics of this. That explains the previous question that we asked. Right? So let's go back. Right? So let's go back here. Right? So that was the question that I asked you to think about. Right? It seems that no matter which k I pick, right, the score is going to be the same, right? I can set k to 1, to 5, 12. The score seems to be the same, right? Why? So now you see why, right? Okay, and it's a score that involves all the paths, right? It's the sum of the scores of all the paths, connecting start and stop, right? And if you further think about what's this score, right? Some people will say, okay, isn't it always 1? The answer is no, right? The score is actually, right, it's from here, it's from, okay, so it's actually px, right? So if you rewrite this, right, it's a conditional probability here, right? If you rewrite this a little bit, you realize that the denominator is actually px, right? So this is exactly px, the probability for that particular input sequence. Okay, right. So let's see if I have something like that here. Okay, maybe not here. Right? Yeah, you should be able to find the px in the previous lectures slides. Okay. All right. So we are now. So we are now here. All right, so we are done with our discussion of the forward-backward algorithm, right? So essentially, it's a dynamic programming-based approach, right? So our conclusion is that we can actually perform the soft EM procedure efficiently, since we can actually perform the forward-backward procedure efficiently, right? And turns out forward-backward procedure can also be used in some other scenarios, right? So it's actually a procedure that's used for inference, but turns out we can also use it for decoding, right? So the question is, how can we use it for the purpose of decoding, right? So recall, what's the setup in decoding? In decoding, you are given the X input sequence, right? And your job is essentially to figure out the Y sequence, right? So we are familiar with this setup, right? So this is essentially what we did in the Viterbi decoding procedure. We want to figure out the optimal Y sequence, right, for a given input X sequence, okay? So that's what we did in Viterbi, right? So the property here with the Viterbi decoding procedure is we have to jointly make a decision, right? We have to figure out what's the globally optimal Y sequence, right? So it's a global decision, right? Okay. Now, there's actually an alternative approach. It's called a max marginal decoding approach. So here in this approach, right, we are also doing decoding. We are also finding the Y sequence. But I'm taking quite a different approach here, right? So instead of taking this global approach, right, I'm going to take a local approach, right? So what does this mean? It means that I'm only looking at one particular position at a time, right? So for example, I look at the first position only, right? I want to figure out what's the most probable Y or the most probable tag, right, for this particular position, right? So the question that I'm asking here is slightly different, right? I'm interested in this conditional probability, right? So then after that, I move to the second place, right? And I ask what's the optimal Y or optimal tag for my second position, right? Given the underlying sequence, input sequence is like this, okay? And I just repeatedly ask the same question n times, right? One for each position, right? And eventually I can concatenate, right? These individual Ys to form the sequence, right? So this is more like a local approach. When I make a decision, I really don't care about other positions, right? I'm kind of more greedy. I'm very selfish. I only look at myself, right? I don't care about others. But this is more like a global approach, right? So empirically, right, using this approach will give you better results. But this is also approach that people use, right? So in fact, in certain cases, in certain scenarios, in some other models, right, turns out it's only feasible for you to perform this approach, right? So that's why, I also want to discuss this decoding approach a little bit. Right? Okay, now let's look at this problem. So we are facing a slightly different problem, right? So previously in Viterbi, this was a problem that we solved, right? So we have an efficient procedure here to perform this kind of decoding, right? So we have a forward pass followed by a backtracking stage, right? But what about this? All right, let's look at this problem, right? So we are looking at a position and we are asking the question, what's the optimal YJ, right, for the given X sequence? Right? Does this look familiar to you? Okay, maybe I should change a little bit here, right? I'm going to say, I assign the value of YJ to U, right? And then I'm going to, find the optimal U here, right? So it's essentially rewriting the previous problem. They're equivalent, right? Okay. Now, does this look familiar to you? This is essentially a problem that we have been discussing, right? In inference. It's an inference problem, right? Right? Okay, how do we rewrite this conditional probability? Okay, if you go back to refer to the slides, you should be able to rewrite it in terms of alpha and beta. Okay. All right. So then you quickly realize that this term has nothing to do with U, right? Okay. So this has nothing to do with U, and we are doing argmax, right? So we can remove it. All right. So our problem becomes something like this. All right. So what does this mean? That means, to perform the max marginal decoding, right? All you need to do is to run the forward-backward algorithm first, right? And then after that, you should be able to know the values for the alpha and betas, right? And then you should be able to take the alpha and beta values, right? And from there, you should be able to make the decision which U is the optimal U that should be assigned or returned, right, at the JS position, right? That should be assigned to the optimal YJ star. Okay, right? So that shows that we can also use the forward-backward algorithm, right, to help us to perform this spatial kind of decoding, right? So that's it's an application of the forward-backward algorithm. All right, so with that, we are essentially done with a hidden Markov model, right? So this is where we are, right? And next, we are going to move into Bayesian networks, right? So in fact, Bayesian networks, right, contains hidden Markov model as a special case, right? In other words, they are more general, okay? So this is going to be the focus of our next lecture, right? But interestingly, right, this is actually more challenging, right, than Bayesian networks, right? They are more general, it doesn't mean they're more challenging, okay? So the topics there would be much simpler, right, as compared to hidden Markov model, right? And also congratulations that you have actually managed to go through the most challenging part, right, of this course. All right, so I'm going to stop here and see you in the next lecture.